Sorry students, I just had to reset the system. So we were discussing about identity arrow, this particular identity arrow, and recall that if A is related with B, then home AB consists of one arrow which is denoted by this particular symbol. So as far as this arrow is concerned with domain A and codomain A as well, note that our reflexive property says that A is related with A. A is related with A. Therefore, there is an arrow from A to A because of our definition. So this particular arrow AA are represented by this symbol is given by the reflexive property. So this arrow is given by reflexive property. By reflexive property or reflexive law is given by reflexive law, which is A is related with A. So therefore home AA is just equal to this particular morphism AA according to our notation. So this is the identity arrow from A to A. Fourth, next we come to composition. So for three elements A, B, C belonging to set P, the function from home AB cross home BC to home AC which means that if A is related with B, then there is an arrow from A to B, and if B is related with C, then there is an arrow from B to C, and this order pair will go to this arrow from A to C, which is given by transitive law, which is given by transitive law, which says that if A is related with B and B is related with C, then A is related with C. You can read it. If there is an arrow from A to B and there is an arrow from A to C, then A is related with B and B is related with C by transitive property gives you A is related with C. So this means that then there is an arrow from A to C. In case you take empty set here and empty set here, you will obtain empty set here. For other cases, you can have empty set here and arrow here, or arrow here and empty set here. for other cases, if it is phi and it is phi, if there is no arrow from A to B, there is no arrow from B to C, then there will be no arrow from A to C. And you can manipulate for other cases as well. So this is the way we define composition of arrows. Next we come to associativity. So for associativity, let A, B, C and D, these are four elements of P which are in fact objects of our category. Then we consider that there is an arrow from A to B. If there is an arrow from A to B, which means that A is related with B. And we compose this arrow with composition of these arrows. B is related with C, or there is arrow from B to C, composed with there is an arrow from C to D, and you can easily see that this is equal to arrow from A to B. That means that A is related with B, composed with B is related with C, composed with C is related with D. By our definition, it becomes B is related with D because of transitive property. So it will become B is related with D. And these two composed with each other will give, by transitive property again, A is related with D. So this is arrow from A to D. And similarly, if we compose these two arrows with each other, we compose this arrow with this arrow BC, and we compose this composition with this arrow CD. This will become, because of transitive property, these two arrows composed with each other will give you AC arrow, that is A is related with C because of transitivity, and then composed with C is related with D. And when we compose these two with each other, we get A is related with D, and you can see that these two are equal, and therefore this is equal to this, and therefore AB arrow composed with composite of BC and CD is equal to composite of AB and BC composed with CD. Therefore, composition is associative. But note that we have discussed only one case. There can be more cases. It may be the case that this is empty or this is empty. You can do with other cases similarly for other cases. Similarly for other cases. Therefore, composition of arrows is associative as well in this case. Composition of arrows is associative as well in this case. So this was associativity. So after associativity, we must discuss composition with identity arrows. So number 6. Finally, we take an arrow AB, arrow from A to B, which belongs to home AB. This arrow exists if A is related with B. Other cases are also which are phi if A is not related with B, but anyway. So let A is related with B, then this is an arrow in home AB. So we compose this arrow AB with this arrow AA. Note that this AA is identity arrow, and you can very easily see by transitivity that this is equal to AB because of our definition. And similarly, if you compose this arrow AB with this arrow BB, then you can see that this is equal to arrow AB. So if you compose identity arrow from left hand side with AB, you get AB. If you compose identity arrow, this particular one, with AB, you again get AB. So that particular law about composition with identity arrows is also valid in this case. Similarly for other cases, because there are other cases as well. Similarly for other cases. So all the conditions have been satisfied, therefore P with this relation, which is pre-ordered relation, therefore this pre-ordered set is a category. So note that every pre-ordered set is a category in which objects are elements of that particular set, and morphisms are the way we have defined, and we have defined that if element A is related with B, then there is one morphism, and if A is not related with B, then there is no morphism. So this is the definition of morphisms for a pre-ordered set. Let me remark that a partially ordered set is also a category. A partially ordered set is also a category. Let me recall that. If you include anti-symmetricity as a condition with two conditions are pre-ordered set, then that pre-ordered set becomes partially ordered. When the set is pre-ordered, then there are only two conditions, reflexivity and transitivity. While for a partially ordered set, there are three conditions, reflexivity, transitivity, and anti-symmetricity. So a partially ordered set is also a category. Now, let's come to the concepts we have discussed in our previous session, and that were about one-to-one functions, about onto functions, and we proved two conditions for one-to-one functions and for onto function. One condition for one-to-one function and one condition for onto function. We are going to come to concepts which are parallel to these conditions in the category theory. So we are going to discuss now epimorphisms, monomorphisms, and isomorphisms. Epimorphism, we mostly write it as epi. Monomorphism, we mostly write it mono. And isomorphism, we mostly write it iso. So we are going to discuss epis, monos, and isos. So let's define first definition. And you will feel that we have done this thing in our previous session in the setting of sets. So a morphism F in the category C a morphism F in the category C and you know that we write C just slightly fancy. So a morphism F in the category C is epimorphism. This is definition of epimorphism. Is epimorphism if for every pair GH if for every pair GH of morphisms in C with G composed with F is equal to H composed with F, we must have G is equal to H. Let me recall the way we wrote it in our previous session. We wrote in this way. G composed with F is equal to H composed with F implies that G is equal to H, and we called it that F is right cancelable. F is right cancelable. That is, F is right cancelable. So this is same thing we have done already in our previous session. So this is the definition of epimorphism. So let's see the example we have discussed in our previous session. Every onto function in the category of sets is epimorphism. We have proved that every onto function in the category of sets we denoted by this particular symbol is epimorphism. Now let's come to next definition. And the definition is of monomorphism. So a morphism F in C is monomorphism. So a morphism in the category C is monomorphism if for every pair GH if for every pair GH of morphisms in C with F circle G is equal to F circle H, we must have G is equal to H. And recall that this is the same condition we have already done. Let me write it here as a note. So what we are saying is that if F circle G is equal to F circle H, then G must be equal to H, which means that is F is left cancelable. F is left cancelable. So if F is epimorphism, then if these two compositions are equal, then F is right cancelable and G is equal to H. And if F is monomorphism and these two compositions are equal, then F is left cancelable and G is equal to H. So this is the definition for epimorphism and this is the definition for monomorphism. And note that these definitions do not depend upon elements. So having said that, so we can have example. Every monomorphism in the category of sets or every one-to-one function in the category of set is monomorphism. So let's write this example. Every one-to-one function in the category set, which is category of sets and functions. So every one-to-one function in set is monomorphism. So now let's come to next definition, and this is definition of isomorphism. So a morphism with the domain A and codomain B. Let's denote this morphism by F. So a morphism F in a category C is isomorphism if and only if there exists a morphism we denote it by F inverse, and this morphism is going to be from B to A. If there exists a morphism from B to A, and we denote this morphism by this particular symbol, and you know this symbol very well, we call it F inverse. So far it is just a symbol, but you can see that this is going to be inverse of this function. So if and only if there exists a morphism which we denote by this particular symbol, such that if we compose F inverse with F, result is equal to identity morphism of A, and if we compose F with F inverse, then the result is identity morphism of B. Let me write it as a note. It is much more easy to understand. Note that F is a morphism with domain A and codomain B. This is F. F inverse is a morphism with domain B and codomain A. So this is F inverse, and their composition will be from A to A. This is their composition from A to A. So this is F inverse composed with F, this, and requirement is this should be equal to identity morphism on A. So this must be equal to identity, and this is the morphism from A to B, which is F. F inverse is from B to A. This is F inverse. Now their composition will be F composed with F inverse. This will be from B to B. This will be from B to B, and this is F composed with F inverse. And this should be equal to identity morphism on B. Identity morphism on B. So this is the condition. If we compose F inverse with F, result is identity morphism of A. And if we compose F with F inverse, result is equal to identity morphism on B. So these diagrams help in understanding. So anyway, a morphism is isomorphism if there exists inverse of that morphism, so that their composition is equal to identity in either case. So this is the definition of isomorphism. Let's just make another definition, that is, if there is an isomorphism from A to B, then we say that A and B are isomorphic. If a morphism with domain A and codomain B, which is, say it is F, is isomorphism, in a category C, then we say that A and B are isomorphic. A and B are isomorphic. And we write it as A is isomorphic with B. And you are very well aware of this concept because you have proved many theorems about two groups being isomorphic with each other, two rings being isomorphic with each other. Maybe you have done similar things with other algebraic structures as well. But anyway, if F is isomorphism, then we say that A and B are isomorphic, and this is the symbol which we use for showing that A and B are isomorphic. Let's come to a proposition. Proposition says that an isomorphism in a category C is epimorphism as well as monomorphism. So an isomorphism in a category C is epimorphism as well as monomorphism. Is epimorphism as well as monomorphism. And it seems quite obvious. What we are saying is that isomorphism is epimorphism and monomorphism as well. If you see in case of sets, what we are saying is a bijective function is onto and one-to-one as well. So this is if we see it in the category of sets. Anyway, so let's see that how this proof goes. So let's prove that. So let's consider an isomorphism. So let A into B be an isomorphism. be an isomorphism in the category C. Then, by definition of isomorphism, we have just defined what isomorphism is. This was definition of isomorphism. Then, by definition of isomorphism, there exists a morphism F inverse such that then there exists a morphism F inverse, or we can write it in this way: F inverse is from B to A. There exists a morphism F inverse from B to A such that these are the two conditions we have written above, such that F inverse let me write it again. F inverse circle F is equal to identity of A. Let's call it 1. And F circle F inverse is equal to identity of B. So this is in fact from the definition of isomorphism. So now we have to prove that this isomorphism F is epimorphism. So suppose that there are morphisms G and H in C such that, suppose there exist morphisms G and H in C such that, remember that in order to prove that a morphism is epimorphism, we have to prove that it is right cancelable. So this is what we have to do. So suppose there are morphisms G and H in C such that their compositions with F are equal. G circle F is equal to H circle F. Then you compose on both sides with F inverse. So H circle F, compose it with F inverse. Now use associative law. So therefore G circle F inverse is equal to H circle F inverse. Now we know that F circle F inverse is equal to identity of B. F circle F inverse is equal to identity of B. Therefore we can write it G circle identity of B is equal to H circle identity of B. And we know that if we compose with identity morphism, result is going to remain the same morphism with which we are composing that identity morphism. Therefore, G is equal to H. So we have proved that if G circle F is equal to H circle F, then G is equal to H, which means that is F is right cancelable. F is right cancelable. And this happens only if the morphism is epimorphism. Therefore, F is epimorphism. So every isomorphism is epimorphism. Secondly, now suppose that there exist morphisms. We use same symbol G because this is another step. If you like, we can change the symbol GH and write KL or something else, but it will be easier and convenient if we use GH again. So suppose that there exist morphisms G and H in C such that F circle G is equal to H circle G. Then, sorry, I'm not writing corrected. F circle G is equal to F circle H. F circle G is equal to F circle H. You can check it by drawing the diagram. So suppose there exists morphism G and H in C such that F circle G is equal to F circle H, then compose on both sides with F inverse. Then F inverse composed with F circle G is equal to F inverse composed with F circle H. And then use associative law. So this is F inverse circle F circle G is equal to F inverse circle F circle H. And therefore we know that F inverse F is equal to identity of A. So this is identity of A. So therefore identity of A composed with G is equal to identity of A composed with H, and therefore G is equal to H, which means if F circle G is equal to F circle H, then F is left cancelable. That is, F is left cancelable. And therefore F is monomorphism. So we have proved that an isomorphism is epimorphism as well as monomorphism. Let's note that in the category of sets, epimorphisms are exactly the onto functions, and monomorphisms are the one-to-one functions, and isomorphisms are the bijective functions. So let's just have a note. In the category of sets, we denote it by SET. So in this category, epimorphisms are exactly the onto functions. And monomorphisms are one-to-one functions. And isomorphisms are bijective functions. So in the category set, the bijective functions are isomorphism. So in set, the bijective functions are isomorphism. The bijective functions which are one-to-one as well as onto. The bijective functions are isomorphism. The bijective functions are isomorphisms. Therefore, every function which is epimorphism as well as monomorphism is isomorphism in the category of sets. So, therefore, every function which is epimorphism as well as monomorphism, onto as well as one-to-one, which is epimorphism as well as monomorphism is isomorphism. In the category of sets. In this, I repeat it again. In the category of sets, every function which is epimorphism as well as monomorphism is isomorphism. When we say in the language of sets, we say that every function which is one-to-one and onto, or every function which is onto as well as one-to-one is bijective function. And in the language of category theory, every function which is epimorphism as well as monomorphism is isomorphism in the category of sets. Remember that this is not a general rule or general law. This is only for the category of sets, that every function which is epimorphism as well as monomorphism is isomorphism, but in the category of sets. So let me write it. F epi as well as mono, F epi as well as mono, mono implies that F is iso, and if F is iso, then F is epi as well as mono, but this is in the category of sets. In this category, it's very important to note this particular thing. In fact, this is not true in general category. In general category, a morphism which is epi as well as mono may not be iso. So let's have this comment. Note, in general, in a category C, in general, in a category C, a morphism which is epi as well as mono need not be iso. So in general, if a morphism is epimorphism as well as monomorphism, it may not be an isomorphism in a general category. To see the example, let's take this particular example of pre-order as a category. So consider the pre-ordered set. Consider the pre-ordered set. We have just discussed it. So consider the pre-ordered set P with relation or pre-order denoted by this particular symbol, and we know that this is a category. We have discussed it in detail, which is a category. Let's take two elements of this partial order set P, which are in fact objects of this category. So let A, B belong to P, which are objects of this category, because every pre-ordered set can be considered as a category. So then, now note that then the map, we denoted it by this symbol. So a map from A to B exists if this map exists. Then the map, this particular map, if exists, in order to say that this map exists, this means that this means that A is related with B. We say that a map from A to B exists if A is related with B. And if A is not related with B, then there is no map from A to B. This is our definition. So the map this, if exists, is always, this is always epi. Now reason for this is because for an object C, which is in fact element of pre-ordered set P, there can be at most one arrow from B to C. Let me say it again. From B to C, there can be at most one arrow. Either there is an arrow from B to C if B is related with C, or there is no arrow from B to C. So we are saying that there can be at most one arrow, this particular arrow from B to C. Therefore, if we compose AB with arrow from B to C. This is one arrow. Now we want to compose A to B with another arrow from B to C. But there is no other arrow from B to C. There is exactly one arrow from B to C. Remember, this is what G is, this is what H is. But since from B to C there is exactly one arrow, so if you take this with on the right hand side, then the same arrow, G and H are same because there cannot be more than one arrows from B to C. So if there is an arrow from B to C, this is the only arrow from B to C. This is the, therefore this composed with G is equal to this composed with H, and G and H are going to be same. This, and therefore this particular thing always implies that these two arrows are equal. These two arrows are equal. They are equal, in fact, because there is no other arrow. Implies that BC taken as G is equal to BC taken as H. Therefore, is happy because this arrow is left cancelable. Therefore, this particular arrow AB is happy. Similarly, we can easily see that AB is mono. Similarly, this arrow AB is mono. But AB is not iso in general. But this AB is not isomorphism, in fact, in general. The reason is AB is iso if A and B are equal, because in this category isomorphism, that was A is contained in A, that reflexive property. So this is iso if A and B are equal. Isomorphism from A to A. This is iso if A and B are equal. Now this particular arrow is epimorphism. This is as well as monomorphism, but this is not isomorphism in general. This will be isomorphism if A and B are equal, but A and B may not be equal. So in the pre-ordered, in the category of pre-ordered set, there are morphisms which are epimorphism and monomorphism but are not isomorphism. So in general, in a category, a morphism which is epi as well as mono may not be iso. So